Think about your favorite apps, like Netflix or Uber. From the outside, they look like one single program, but behind the scenes, they are actually a pulsing network of hundreds of smaller, independent programs working together. We call these smaller programs microservices. Because different teams build these microservices, they are often written in entirely different programming languages. One team might build a piece in Java, while another uses Python, and a third works in C++. To make the app actually work for you, these pieces have to talk to each other constantly. The video delivery system has to ask the user profile system what you're watching, and the billing system has to confirm your account is active. In this environment, the overall user experience relies on how efficiently these different languages communicate across the network. For a long time, the standard way to make these services talk has been the REST API. You can think of a REST API like mailing physical, handwritten postcards between different job sites. The language written on those postcards is usually JSON. JSON is great because it is easy for humans to read, but for computers, reading and writing all that text is bulky and slow. There's also a built-in waiting period. With the postcard method, a system sends a request and then has to sit completely idle, waiting until the full response makes its way back in the mail. When you scale this up to massive systems processing millions of actions a second, the bulkiness of the text and the constant waiting around create significant delays. That's why engineers created gRPC. If the old way was mailing postcards, gRPC is a high-speed, unified radio system built specifically for massive, multilingual software projects. The foundation of gRPC is something called protocol buffers, or protobufs. Before anyone writes a line of code, the teams use this as an agreed-upon blueprint that defines exactly how their data will be structured. Once that blueprint is set, gRPC uses it to automatically generate the exact translation code each microservice needs in its own native language. Instead of bulky text, protobufs compress the data down into a microscopic binary format. Computers can read this binary format almost instantly. This approach bridges the gap between different programming languages while shrinking data payloads so they can move across the network as fast as possible. The RPC in gRPC stands for Remote Procedure Call. The old method was like asking a waiter to fetch your order. An RPC acts more like a direct remote control. With this remote control, a program written in Python can push a button and instantly trigger a specific function inside a Java program, even if that Java program is running on a server halfway around the world. For the software developer, calling a distant server becomes as simple and direct as running code right on their own local laptop. This chart shows gRPC's 4 data flows on HTTP2's multi-lane highway. Server streaming sends continuous updates, like a stock ticker. Client streaming uploads massive files in chunks. Bidirectional streaming lets both send continuous rivers of data simultaneously, essential for multiplayer gaming. By keeping a single connection continuously open, this streaming ability removes the repetitive setup steps and idle waiting times that slow down traditional connections. To keep this high-speed traffic organized, gRPC uses tools like interceptors. Think of them as security guards at the gates of a construction site. They check authentication badges and log who comes in before any data is allowed to pass. There are also strict countdown timers called deadlines. If a server is running too slow, the deadline forces the client to abandon the request. This stops the rest of the application from freezing up while waiting for a single slow piece. This chart shows a unique risk with gRPC's long-lived connections. You can see the dots, which represent data requests, clustering heavily on just the bottom 2 rows. Without proper management, traffic pools on a few overloaded servers, while others sit idle. This next chart shows how adding an ingress controller, which acts like an intelligent traffic dispatcher, fixes the problem. It actively distributes the incoming requests so that the blue and orange dots are evenly spaced across all available servers. These 3 tools, interceptors, deadlines, and load balancing, are what turn a fast protocol into a reliable foundation for large-scale applications. You might be wondering, if gRPC is so efficient, why hasn't it replaced the old postcard method on every standard public website? The main reason is that standard web browsers, like Chrome or Safari, cannot natively read gRPC's complex binary traffic without adding specialized workarounds. For public-facing web pages, where human readability and broad browser compatibility are the top priorities, the older combination of REST and JSON is still the standard choice. gRPC's true home is the hidden nervous system of an application. It thrives in the internal backend, where servers must communicate continuously with other servers. Between the protobuf blueprint, the remote control mechanism, and the high-speed data highway, gRPC provides a powerful way to connect dozens of different programming languages. You will probably never see gRPC directly when you open an app on your phone, but underneath the surface, it is the invisible, heavy-duty engine that keeps our most complex digital systems running smoothly. Thanks for watching, and be sure to like and subscribe for more deep dives into the technology that runs our world.